Hey everyone, welcome back. In this video, we're going to talk about ellipses. And so let's go ahead and start with our geometric definition of what an ellipse is. And our definition is actually going to be pretty similar, although I think somewhat harder to digest than the geometric definition that we had for a circle. And so our definition that we'll start off with for an ellipse is the set of all points x and y, the sum of whose distance from two fixed points that we call f1 and f2 is constant. These two fixed points, f1 and f2, are referred to as the foci of the ellipse. Foci is just the plural of focus, and the midpoint between the two foci gives us the center of our ellipse. So how do we go about drawing an ellipse? Well, we start with not our center point like we did with our circle, but our focal points, f1 and f2. And so let's go ahead and say this green point is just one point that is on the ellipse created by our situation here. And so what we know about this green point is that if we were to measure the straight line distance from the green point to our first focus, f1, and we also measured the straight line distance from our green point on our ellipse to our second foci, f2. Remember, the foci, like the centers of the circle, are not actually on the ellipse. They're just these useful points that help us create the shape. The green point is a point that is actually on our ellipse. And so let's go ahead and call that first distance d1 and that second distance d2. And so the way we can go from this first point on the ellipse to any other point on the ellipse is using the fact that the ellipse is the set of all points, the sum of whose distance from f1 and f2 is constant. So what does that mean for us here in our picture? That means if we were to add up d1 and d2, we get a number, and that's going to always be a constant number that does not change. Meaning, if we were to make d1 a little bit smaller, that would have to come at a cost. The cost d2 would have to get bigger, because these two numbers, d1 plus d2, have to always give us the same constant number. Now, it's really hard to kind of visualize, well, what's another point on the plane that's going to have the distance from f1 and f2 equal the same as the sum of the distances of d1 and d2 that we have here. Very hard to draw without some kind of drawing aid. But if you have a piece of string, it's actually very easy to draw an ellipse. All you have to do is decide the length of your string. What's the length of your string going to be? It's going to be that distance d1 plus d2. You then put the ends of your string at the fixed points f1 and f2, and then use your pen to make that string tight or taut. And then as you try to pull that string away and move around, you will end up drawing the ellipse. Let me go ahead and try to do that here. Let me try to do it in green. And so maybe our ellipse would look something like this. I'm sure this is not a true ellipse because I drew it by hand without a string. But the idea is, now if we were to look at some other point on our ellipse, like maybe this green point down here. If this was a true ellipse, then this point, let's go ahead and call it, well, we're using D1 and D2, maybe capital D1 and capital D2. Then big D1 plus big D2 would be the same as little d1 plus little d2, even though these d1s and d2s are not at all equal. So I don't have a good setup on the Lightboard to kind of get some strings up here and draw the ellipse by hand, but I can have a computer-generated animation help us visualize this process of drawing an ellipse. And so now we can see in the animation, as we move around and traverse the ellipse itself, those straight lines representing the distance from our foci to the point on our ellipse, all those straight lines are constantly changing and doing basically a balancing act. Doing this balancing act so that the sum of the lengths of those two lines is always the same number. That seems like maybe a weird way to describe a shape, not a very modern way to describe a shape, but we have to remember this stuff was studied a very long time ago, even before they had algebraic descriptions. So using something like a string and this argument of these sum of these two fixed distances is constant actually gives a really effective way to communicate how to draw this elliptical shape. And we aren't going to spend too much time looking at the applications of the foci of an ellipse here. But there are some really incredible physical applications that you can get into when looking at the foci of an ellipse. The idea is if we had an elliptical shaped chamber or room or something like that, then all these sound or light waves or any type of waves that are emanating from one of our foci are going to bounce off the walls and become concentrated at the second foci. This is an important property for acoustics that can be taken advantage of, and it also has some really important applications in medicine and treating things like kidney stones. What doctors can do is they have these elliptical shaped, basically like bathtubs that a patient can sit in with a kidney stone. They'll kind of orient the patient in that tub so that the kidney stone is at one of the focal points, like F1. And then what they do is they place something like a ultrasound at the other focus point, and then the sound waves bounce off the chamber and all get focused at the location of that kidney stone, which allows all those non-damaging sound waves at their own to kind of be concentrated and break apart that kidney stone, which allows the patient to have their kidney stone taken care of without having some kind of invasive operation. So I think that's probably the coolest application of an ellipse that I've heard of. Of course, there's tons of other ones. Probably some of the first applications of an ellipse, though, were like describing planetary orbits. So it might seem like kind of a weird shape looking at the geometric definition, but it's a really useful shape. It shows up all over math and science. And so the idea is, if these two shapes were ellipses, then they'd have foci F1 and F2, and the orientation of those foci would be approximately in the locations that I have graphed them in. All right, so the center of a circle was one of those important points that we needed in order to graph or work with the equation for our circle. Something similar we're going to see is happening with an ellipse. So where is the center of our ellipse going to be at? It's the midpoint right between those foci. And so these pink dots are the center of the ellipses. If you know the x and y coordinates of your foci, you can just find the average of those for each the x and the y, and that'll always give you the center of your ellipse. So there's a couple other important bits of terminology that we need when we're describing and working with our ellipses. And one of those are the major and minor axes of an ellipse. And so all the ellipses we're going to look at are always going to be sort of either kind of short and fat or thin and tall. If our ellipse is wider than it is tall, then that horizontal line running across the middle of our ellipse through the two foci and the center point is what we call the major axis of our ellipse. And if our ellipse is more tall than it is thin, we still have a major axis, but now it'll be a vertical major axis. Perpendicular to the major axis will be the minor axis. So if we have a horizontal major axis, then we'll have a vertical minor axis. And if we have a vertical major axis, then we're going to have a horizontal minor axis, right? You can always kind of measure the two axes. The longer one is the major one. The smaller one is the minor one. They're very aptly named. And then one last little bit of terminology for now are these kind of points that might show up when given descriptions of our ellipses. And so these points that are at the end of our major axis, depending on our orientation, are going to be referred to as the vertex or vertices of our ellipse. So when it comes to graphing the ellipse, we're going to want that kind of oval shape that is the actual ellipse, but included in our graphs, we're going to want things like the center, the foci, and once we have those, we can use things like the center point or the foci, then find the vertices on the major axis, and similarly, the vertices on the minor axis. Putting that all together, kind of generating those 4 points along with the foci in the center will help us sketch our ellipse. Up next, we're going to talk about how we can go from our geometric description of an ellipse to a kind of algebraic or symbolic description of an ellipse using an equation. All right, so to help us go from the definition of an ellipse to the equation of an ellipse, I'm going to go ahead and draw this general ellipse here, but it's not a totally general ellipse because we're going to assume that its center is at the origin 0, 0. But we'll talk about shifted ellipses with these non-origin centers right after this. And so I've also labeled a bunch of these important points, and some of these values will show up in the equation that we're going to talk about deriving here in a second. So the ellipse is centered at the origin 0, 0. The foci are going to be on the major axis. I'm assuming here that the major axis is horizontal or on the x-axis. Things might change a bit if the major axis was on the vertical axis or y-axis. That change where our focal points are at. But since our focal points are on this horizontal major axis, we know their y-coordinates would have to be 0 in this setup. And then I'm just go ahead and labeling their x-coordinates as negative c and positive c. We know we have this type of symmetry between the foci because our center is at the origin and the center is the middle point or midpoint between the foci. The other points I have labeled are the vertices on the major axis. I'm going ahead and call those A0 and negative A0. And then the also vertices on the minor axis, which are getting called 0b and 0 negative b. And so when we were deriving the equation of our circle, we used that fact that the circle is the set of all points whose distance from the center is constant. Well, for an ellipse is the set of all points, the sum of whose distance from the foci is constant instead. And so when we were talking about that earlier, we said if we looked at D1 and added that to D2 for any point on our ellipse, it's always going to give us the same number. So let's go ahead and start deriving the equation of our ellipse by thinking of, well, what is the sum of our distance D1 and D2 going to look like? Well, in our picture here, what we can see is it's always going to actually be equal to 2 times A. We can really quickly verify that D1 plus D2 is in fact equal to 2A. Well, we're going to try not to get too lost in the weeds here, but remember, D1 is the distance from our focus to one point on our ellipse. Let's go ahead and focus on that vertex point at A0. So what is the distance between C0 and A0? Well, that distance is going to be this horizontal distance, just A minus C. So that is like our D1. We have to add to that D2, the distance from our other focus point to our vertex point of interest here, A0. Well, we have to go from the origin, A units to get to A0. And then we have this extra horizontal distance, which is C units just in the negative direction. So we have to go C units plus A units to get from our second foci to the point A0. So that'll be A plus C. But now if we add D1 and D2 together, the C's cancel out. We get 2 like terms of A. So we do in fact get 2A. And so the algebra is going to get pretty intense here. We're just going to get it kind of started, then skip over a lot of the busy work, but we're still going to set things up. And so now if we want to continue to set things up, we need to describe these distances D1 and D2 in terms of some of these constant quantities that we might know, like A, B, and C. Well, we know that we can find D1 or D2 using the Pythagorean theorem or the distance formula. So D1 will be the square root of the sums of the squares of the difference between the x and y coordinates for the 2 corresponding points. Those are going to be negative C0 and xy. So the difference between our x coordinates is going to be x minus negative c, or that'll be x plus c squared. And the difference between our y coordinates will be y minus 0, or just y squared. And our expression for the distance D2 would look like, again, the difference between the x coordinates squared would look like x minus c squared, and the difference between our y coordinates squared would again look like y minus 0 squared. So then we can plug this expression for D1 into our equation that defines an ellipse, or that important relationship between points on our ellipse. So D1 plus D2 is equal to 2A, right? Just using that fact from the definition of an ellipse, that an ellipse is the set of all points, the sum of whose distance from 2 fixed points, that's what these 2 square root expressions are describing, the sum of those 2 distances from the fixed points that we call the center, that equals some constant that we found to be called 2A, or the length of our major axis. And so now how do we derive the rest of our equation? Well, we do a lot of tedious algebra, right? We got to kind of square both sides, but then we still get a square root, so we got to square again, move things around. It can get a bit intense, and a lot of time can be spent going through all that algebra, but that algebra is not super necessary to go through because we're really just trying to get a kind of standard equation for an ellipse. And if we do take the time to go through all that algebra, what we end up with is an equation of the form x squared over a squared plus y squared over the quantity a squared minus c squared is equal to 1. And we sort of introduced b already earlier in our picture, but it hasn't really shown up in our derivation yet. And the full derivation is we define b as this number, or b squared as this number, a squared minus c squared. And we can also argue or show that that value of b will also help us find the vertex on the minor axis. So if we do make the substitution, let this quantity a squared minus c squared be represented by this number b squared instead, then our ellipse will have an equation of the form x squared over a squared plus y squared over b squared is equal to 1. So this is our kind of standard form only for when our ellipse is centered at the origin. But from the standard form, we can use those a squared and b squared values to find a and b, help us find the vertices on the major and minor axis. And then once we have a and b, we can also find c, which helps us locate the foci, which are also always on that major axis. So besides skipping over all this busy work with all this algebra, we basically derived together the standard form for an ellipse centered at the origin 0, 0. Now let's go ahead and talk about what does the standard form for an ellipse not centered at the origin look like. So in our discussion so far, we've kind of talked about how to derive the standard form for an ellipse that is centered at the origin 0, 0 with the assumption that it has a horizontal major axis of length 2a and a vertical minor axis of length 2b. And that's what our picture and equation is going to look like over here. So that equation would be of the form x squared over a squared plus y squared over b squared is equal to 1. So a is used for the major axis here. If we have a horizontal major axis and we haven't shifted away the center from being at the origin, then the points or the vertices at the end of the major axis will be negative a0 and a0. And the points at the end of the minor axis will be 0b and 0 negative b. So it's very easy and quick from the equation to find a and b and find the 4 vertices that make up our ellipse. Those 4 points are pretty much really all we need to sketch the shape of our ellipse, but we're often going to also be asked to find the foci of the ellipse. And to help us find the foci of our ellipse, or that c value, that is the distance we have to go from the center to get to our foci, we just have to remember that relationship that b squared is equal to a squared minus c squared, or c squared is equal to a squared minus b squared. That applies for both of these setups that we see here. So this first setup is what we looked at initially, where we had that horizontal major axis. The second setup is now assuming that we have a vertical major axis. And the only difference that happens is the roles of a and b switch. So we're always assuming that a is our larger number here. So the larger denominator in this kind of elliptical equation setup will help you determine which axis is going to be your major axis. So if we have a bigger number underneath y squared, we're going to have a vertical major axis. If we have a bigger number underneath x squared, compared to the y squared term that is, if we have a bigger number underneath x squared, we're going to have a horizontal major axis. And so it's a really important note that I want to emphasize. The foci is always going to be c units from the center of our ellipse. We can find the center using any kind of pair of vertices. It's always the midpoint, or you can, if you know the foci, you can find the midpoint there too. The foci is always this special number c units away from the center, and the foci always land on the major axis. All right, so everything we have written up on the board is for standard forms of ellipses where a is greater than b and the center is still at the origin 0, 0. But now let's go ahead and change things a little bit. Instead of having the center be at a special point like the origin 0, 0, let's let it be at any point. Let's go ahead and call that center point h, k, just like what we did for circles. Well, now if we are centered at the point hk instead of the point 0, 0, we're going to have to go through and change our equations and our points in all of our pictures. But it's not going to be too difficult of a change to make because we can just use our knowledge of transformations of functions, right? We can think of, instead of centering the ellipse at the point 0, 0, centering it at the point HK is just the same thing as taking our ellipse centered at the origin and shifting it h units in the x direction and k units in the y direction. So how's that going to affect that first equation we looked at for our ellipse when we had a horizontal major axis? Well, if we want to shift it h units in the x direction, we have to replace x with the quantity x minus h in parentheses. And if we want to shift our ellipse or any function k units in the y direction, then we just replace all the y's with the quantity y minus k. And that'll give us this version of our equation, the quantity x minus h squared over a squared plus the quantity y minus k squared over b squared is always equal to 1. Well, now these points that we have currently labeled are no longer accurate because our center is no longer the origin. Now our center is the point h comma k. So we're going to have to add h to all these x coordinates and add k to all these y coordinates. And so if we go ahead and adjust the remaining special points on our ellipse that we see here, adding h to all the x coordinates and k to all the y coordinates, this is what we end up with. Our major axis left endpoint is going to be negative a plus h comma k. The right endpoint on the major axis will be a plus h for the x coordinate and k for the y coordinate, and then so on. Personally, I do not think it is worth kind of memorizing or going back to this kind of negative a plus h comma k. Most general setup, I think it's better to memorize that setup when we're centered at the origin. Then once you do that and know those points, then shift everything corresponding to your new center at hk. Just add your h and k value to all those x and y coordinates respectively. And of course, we have to make the exact same corresponding changes over here for our other equation and graph when we have a vertical major axis. All right, so after making all those changes, this is what we end up with, right? Again, we just replaced x with the quantity x minus h and y with the quantity y minus k for that kind of standard form for an ellipse with a vertical major axis. And by shifting our equation, h units in the x direction and k units in the y direction, we have to also shift all those points. So every x coordinate from our previous graph, I just added h to, right? You can go and check, I crossed them all out so you can still kind of see them. And then all the y coordinates, I just shifted k units by adding k to them. So the thing we want to take away from this are these are the kind of two most general forms that we'll see our elliptical equations in. The larger denominator determines what our major axis is going to be. Once we have that, we can use the numerators to help us find the center. Then we can find the endpoints of our major and minor axes using a and b, using the relationship that b squared is equal to a squared minus c squared. We can then find c. And so once we find the center, those four special vertices and the foci, that's more than enough information to sketch the graph of an ellipse.